Welcome. This lecture is a continuation of my previous lecture in which I started telling you about some of the selective methods for solving nonlinear algebraic equations, and this method will be looking into a few more of these numerical methods to solve the nonlinear algebraic equations. So, in this lecture we shall be studying those few more methods to solve nonlinear algebraic equation, and then we shall also take a special case of solving the cubic equation of state, and we shall be ending this lecture with some knowledge about how to figure out the convergence of a solution. So, this particular thing, it is kind of a carryover from my last lecture in which I started with Newton-Raphson method, and as I told you that the Newton-Raphson method is a very fast fast method, and it needs very efficient, but only thing is this, it becomes cumbersome because at each step you have to calculate the derivative of the function at the new estimated point. Now, in this figure I am just showing pictorially how the Newton-Raphson method works in terms of the solution convergence. So, here we are choosing these two axes, that is fx is that function which we have to, for which we need to find the root, and this is the independent variable, and here we have put one arbitrary function shown by this solid line, solid black line. Now, we start with some initial value, say xn, okay, and we have to reach this particular value, this is a solution, okay. So, we will start with this guess value, and at this guess value what we do, we find the value of the function, that is fxn, and by doing the derivative what we are finding, basically we are finding the slope of this tangent to this particular function at this particular value of the xn, okay. And once we find the tangent at this point, and we see where the tangent is crossing this x axis, okay, that is taken to be the next updated value of the root, okay. So, by doing the calculations as I shown you in my last lecture, we are approaching this xn plus 1. Just for your remembrance, I just put the equation for you again, that x k plus 1 is equal to x k minus f x k divided by f prime x k. Okay. So, this is the recurrence formula for the Newton-Raphson method. So, using this particular formula, we are able to update the value of the root. So, here we are not taking xk, we are putting them in this particular thing is taken to be say xn, and this is taken to be say xn plus 1, okay. And from this we are going towards xn plus 2, and then xn plus 3, and so on and so forth, okay. This continues until we reach convergence, okay. So, now we find the next best value, and again we, from this xn plus 1, again we find out the value of the function, and again we put the tangent over here, and this f dash prime xn plus 1 is the derivative, that is tangent to this, and from this again we find we are going to the another updated value, that is xn plus 2. And now, if we keep continuing this thing, we find that from this particular guess value we are approaching the solution, and we again stop the solution when our convergence criterion is met, okay. So, this is the pictorial representation of the Newton-Raphson method. Now, we go to another method, secant method. In this method, you will find that here also we need to find out the derivative but in a different manner, okay. In this case, in the Newton-Raphson method, we are finding the derivative of the tangent, whereas in this particular method we are finding the derivative of a secant. Perhaps you know that the difference between tangent and secant, just for your remembrance, let me put it for you. So, suppose you consider a given curve, and suppose we have some curve. So at a given point, if you are plotting this thing, this is the tangent. Okay, but on the other hand, if you have some other segment of the curve, so this is the secant. This is the secant and this is the tangent. So as the name of the method suggests you that in this particular method we are considering the secant and we are going to find out the derivative of the secant, and derivative can be found out of the secant if I know this particular point and I know this particular point. That means what? That in case of Newton-Raphson method we were using only one point. Okay. On the other hand, for the secant method to be implemented, we need 2 points, okay, to find out the slope. That means in case of Newton-Raphson method, we need only one starting value, whereas in case of secant method, we need 2 starting values. Okay, and again these 2 starting values can be arbitrarily chosen. So that is why you find that we need 2 function evaluations instead of 1 function evaluation in case of Newton-Raphson method. On the other hand, we need the derivative evaluation in Newton-Raphson method that is not needed in secant method. Okay. Now once we choose, say we start with 2 initial values, say xk and xk plus 1. Now again you see that this fxk plus 1 minus fxk divided by xk plus 1 minus xk, this gives us the derivative of this particular or slope of this particular secant. Okay. So we are using the similar kind of formula as the Newton-Raphson method, only replacing the f prime xk by this particular formula, and rest of the equation, rest of the solution method is same, that once we find this updated value of this xk plus 2, we replace the xk with the xk plus 1 and xk plus 1 with xk plus 2, and we find xk plus 3. Okay. And then after finding xk plus 3, we replace xk plus 1 by xk plus 2 and xk plus 2 by xk plus 3, and we get xk plus 4. So this is the way keep doing this particular thing, and we go towards the solution. It is found that it is slower than the Newton-Raphson, but it is more stable. By stable we mean that how robust it is, a particular method is, so that it does not diverge when we are choosing some arbitrary value for the roots. Okay. So it is found to be more stable, but it is slower than the Newton-Raphson method, and it does not need bracketing of the root. That means we do not need, as we learnt earlier in the bisection method, we needed to bracket the roots between so that the root is between 2 range we are choosing. In this case also we do not need, like Newton-Raphson method, we do not need to bracket the root. Next we go to regular falsi method, that is also sometimes called the method of false position. It is similar to secant method. Only difference is this, that in this case this is the first 2 guesses have to bracket the root. So this is similar to the bisection search. Okay. So in this case again we are starting with 2 values, but these 2 values will be bracketing the root. Okay. So if we know the root, have some idea of the root, then this method should be used. Okay. Now in this case what happens is that whenever we are bracketing the root and whenever we are updating this value of the root, then what we find that how we are replacing the previous 2 values will be depending on the products of the functions at these various points. So first is this to bracket. For bracketing criterion is this, that the product of the fx1 and fx2, these 1, 2 represent the initial 2 values. This product should be less than 0. Okay, that means we are bracketing, and this was the same thing we were using in case of the bisection search. Okay, and after this we are going to check that whether this updated value is bracketing the root or not. Okay. For checking that, again we find out the product of the function values at this k plus 1 and k plus 2 and k plus 2. Okay, depending on the sign of the product, again we reassign the values of xk to either xk plus 2 or xk1 to xk plus 2. So, depending on that. So, let us look pictorially in this particular thing, that in case of regular falsi, what we are finding that initially we start with the bracketing of roots. Suppose x0 and x1 are the two initial values, and we can see that at x1 fx1 is here and x0 fx0 is here. So, when we take the product of these two, we find this is coming to negative. That shows that the root is bracketed between x0 and x1, and you can see here also the root is somewhere here. Then what we do after application of the formula, we get the value of x2. Now again we take the product of fx2 with fx0 and fx2 with fx1. Now you can see here that fx2 and into fx0 will give you positive, okay, but fx2 into fx1 give you negative. So we should replace x0 with x2 and again find out the next root as x3. Now again you can see here that fx3 and fx2 is giving you positive, whereas fx3 into fx1 giving negative. So again the next root should be with this x3 and x1. Okay, so this is the way you can see that we are able to approach the solution. On the other hand, if you look at the secant method, you can see that here the root is somewhere here, whereas we are starting arbitrarily away from the root, and you can see both the roots are on the higher side of this actual value. Okay, but it does not matter. Again we are finding these two function values, and even with this we are finding that we are approaching the roots. So we are getting x2 here, again with x2 x1 we are finding x3 here, with x3 x2 we can again find the x4 here, and like that we are able to approach the solution. Okay, so these are the basic differences between regular falsi and the secant method. Now for a typical problem, you can see that how typically these four methods differ in their convergence characteristics, means that how fast they converge and how many iterations they will take to converge. So here you can see that bisection method is giving, it is also converging but with some fluctuations. That means it is not converging monotonically. Sometimes it is decreasing, this error is decreasing, again increasing, again fluctuating. This way it is going to convergence, and it is taking say about say 20 iterations. Now when you go to method of false position, even though you are bracketing the root, that is the regular falsi method, you say that it is also converging monotonically and it is better than bisection method. Okay, that means in both regular falsi method and bisection search, even though there is bracketing, but the bracketing is not really increasing the speed. On the contrary, if you look at secant method or the Newton-Raphson method, we did not try to bracket the root. Here we are finding the convergence is much faster. So secant method is giving faster convergence even than the regular falsi, and Newton-Raphson method gives us the fastest convergence. Okay, so this is the typical convergence characteristics of these four methods. After knowing this, what we can do, that now we shall go to another special situation, that is of the cubic equation of state. Now even though it is cubic and we have learnt all these methods to solve the nonlinear algebraic equation, but it is a special case because in this cubic equation of state we are basically trying to figure out the properties of the two phases, that is vapor and liquid, that may be coexisting, and even to ascertain whether the particular at the particular temperature pressure we are having only one phase or two phase, all these things. So for this we are adopting some special method, and cubic equation of state, there are many of them. Van der Waals force is the first one which was proposed, and later many such kind of things came. Schwav, Redlich, Kwong, these are names of three scientists. Then Peng, Robinson, the names of two scientists. So by their name also we have many cubic equation of state. Okay, and the general form you will find that these are the general form of the any cubic equation of state, and what will be differing is this: the value of this delta 1, delta 2, A and B, and this B. This B delta 1, delta 2 will be changing for, and this A value will be changing for the various equations of state. So without bothering about what exact form of this A, B, delta 1, delta 2 are, we can still evolve some general method of solution for this equation of state. So, if we define the compressibility factor as Z with PV by RT, then we can reduce this particular equation in this type of cubic polynomial. Okay, and in this we shall be having this d1, d2, d3 as real values. Okay, so there will not be any imaginary values of these coefficients. However, please mind it, the Z may go imaginary. Now, there is one method, one of the methods, there are several methods proposed in the literature. This is one of the methods I am showing you. So, here this Cardano's method, and what is it that we find some this thing, this will be R. Okay. Now, we have these two parameters again we define in terms of the d1, d2 and d3. So, these are the two parameters we define in these two terms, and based on these two parameter values we shall be finding the roots. Okay. So, without going into the derivation of this, we shall be going to the final solution. So, here it is that if r square is less than q cube, okay, Cardano proposed these are the three roots of the equation, and here it has been defined in terms of q and d1, and we have theta here. Theta is defined in terms of r and q. Okay. So, this is for the case when r square is less than or equal to q cube, and if r square is more than q cube, then we have this set of solutions for the x1, x2, x3. Again here we find we have a and b, and these a and b have been defined here. Okay. So, we can straight away use this set of solutions for the cubic equation of state. However, I must mention that this is one of the previous methods. Later on, many modifications were done for this method, and here I just want to mention one thing, that SGN shows the sign. Okay. So, this whatever value of r you get, you have to pick up the sign of r. Okay. This is the meaning of this particular operator. Next, we come to the convergence of the solution. Now, for convergence, whenever you are doing this, again I am giving you any very briefly some idea of the convergence. First, you have to know the significant digits of the solution. Now, what it means? What it means that these are those values that can be used with confidence. Okay, and generally it depends on the least count of the instrument when you are doing some measurement. Now, you have to see that whenever you are solving some problem, you should be understanding that when you report any result, that those results, they should make some physical meaning. Okay. Now, suppose you are measuring temperature, okay, with a thermometer. Now, if the thermometer, if you are talking about the thermometer which we use in at our home to measure the fever, in that case what you find? That the thermometer has a least count of 0.2 degrees Fahrenheit. Okay, you measure like 98, 98.2, 98.4, like that you measure. That means what? Whenever you are reporting or you are calculating the temperature of our body, you should not mention it like 98.4675. Now, this after 98.4675, these are immaterial, because this 675 cannot be verified by your thermometer. So, in that case, you should better restrict yourself only to one significant digit, that we call this 98.4, we call it only these three are the significant digits for the solution or whatever you are reporting. Okay. So, this is what I said, that by what I meant by saying that it depends on the least count of the instrument. So, as you keep on increasing the least count of the instrument, that means we are increasing accuracy of the instrument, you find the number of significant digits also starts increasing. Okay. Next is precision. One is precision, one is accuracy. That is precision. What we mean by precision? Precision means that whenever we are computing the values in the iteration, we should see that each consecutive value, whether these consecutive values are nearly equal or not. Okay. Now, if they are very equal, that means after each iteration, when I am checking the closeness of the consecutive values, if I find that they are very, very close, then we can say that we are approaching the precise result. On the other hand, we have accuracy. Now, accuracy tells us that how close we are to the true value, actual value. Now, it may be so that we are having precise solution. That means, after each consecutive iterations, the values are very close. But these close values need not mean that they are also the true values. Okay? So, that is the difference between the precision and accuracy. And let us see by this particular diagram. Here we have shown those games we play, that where we have to either with the rifle or pistol we have to hit some target. So, let us assume here that the center of this particular thing, the bullseye we call it. So, the center is the where you want to hit it. Okay. Now, we have shown you 4 cases. Now, here you can see in the first case you can see that most of these things are away from the actual center of this thing. Okay. This one is near the center, but it is not exactly at the center. So, we can say all these solutions are imprecise as well as inaccurate. Okay. On the other hand, when you come to this one, what you find here that at least one of them has hit the exact center of the bullseye. Okay. That means our solution is accurate but imprecise. Okay. Because other things are very scattered. Now, you look at the third one. In third one, what you find that all these solutions, the consecutive solutions, are almost nearby, they are clustering nearby. So, but all those things are very much away from the exact solution, from the center. Okay? So, this we call they are precise but not accurate. On the other hand, you look at this, we find that the solution, we are reaching solution, one thing, and second thing is this, all the consecutive values of the roots we are finding, all they are very much close to the actual solution. So, we say this is precise as well as accurate. So, this is the way you can look at precision and accuracy of the solutions. And here I show some commonly criteria of convergence for precision check. Okay? That means when you do not know the true value of the solution, so you check for precision, and then you can also stop your solution, means you can say it is converging. So, something can be absolute error. That means you take simply the difference between the two consecutive values of the root. Okay? And here I am showing xi because there could be more than one equation you are solving for. Okay? So, it should be applicable for all the equations. Next will be relative error, and this means that the absolute error divided by the value in the previous iteration level. Okay? So, this is the relative error, and then we have percentage error, it is the relative error into 100, and here I have put the convergence criterion, that is user defined, and this T shows it is for the approximate values. Okay? And here we have for the accuracy check. Now, here we are putting if I know true value. If you know true value, then what I should do? I should always check, instead of the two consecutive values, we can check always with the true value. It is similar to this one, and again we shall have some kind of user defined criterion, and these are the same as this one. Okay? Only thing is this, here we can have another one, that is we check the value with respect to the function. So, if even we can put for accuracy, we can also put a convergence criterion for the function. Okay? So, each time we are finding some new value, what we do? We put the value in the function here and check whether the function value ideally should be 0, but whether how much near to the value of the function we are approaching. So, that is the way we are putting this accuracy check. So, these are the general methods of locating the convergence of a given solution technique. So, for general, it is given that to get a result correct at least up for n significant digits, this is the criterion that has been prescribed in the literature for these particular values of epsilon. So, more of these you can find out in these references. Thank you.